All right, so let's jump into this world of quantum computing, huh? Today, we're going to be looking at QuEra's Aquila. It's a 256 qubit system, and it's really making some noise in the field. You know, you sent over Jörg-Owe's essay, and we're really excited to kind of break down some of the more interesting points for you.
Yeah. I think one of the things that makes Aquila so fascinating is it's kind of taken a different approach than a lot of other quantum computers out there, Instead of using superconducting qubits, it's using neutral atoms, and that's a pretty big deal.
It definitely caught my eye, I'll tell you that. Schnepp points out that neutral atoms, they kind of offer better control and experience less noise, which I understand are kind of huge hurdles in quantum computing. Can you maybe break down why that's so important?
Sure. It really all comes down to the stability of these quantum states, Like, imagine you're trying to build a house of cards on a table, but the table's vibrating like crazy, right? That's kind of what it's like working with superconducting qubits. They're just incredibly sensitive to any kind of disturbance.
Oh, I see.
Neutral atoms, on the other hand, they're more like building with Legos on a nice stable surface. Much easier to manage, much less prone to falling apart.
Okay. So that's how they're able to achieve that better control and reduce the noise, huh? It makes sense why that would be such a significant advantage then. Now, Schnepp also mentions Aquila's unique architecture. He describes it as a zoned chessboard. What's the significance of that?
Yeah, that's a really, really interesting part of this, I think. So this zoned chessboard architecture is all about efficiency, right? You've got some zones that are designated for storage where the qubits can just kind of hang out, maintain their quantum state. But here's the cool part, right? You can actually move the qubits around for calculations. Think of it kind of like a quantum taxi service, right? Shuttling qubits between storage and these computation zones.
Oh, that's a pretty cool way to visualize it. So they're not fixed in place then. The qubits can be moved around strategically. What kind of impact does this shuttling have on Aquila's capabilities?
Well, it's a game changer, right? It's a game changer in a couple of ways, at least. For one, by moving the qubits around, you can entangle them in very specific ways, and that's crucial for, performing these really complex calculations. But it also allows for much more efficient error correction because you can basically move qubits to these designated zones specifically for that process. And so this kind of flexibility, I think it's really essential for, scaling up quantum computers and making them much more reliable.
That makes a lot of sense. Now, Schnepp also emphasizes this shuttling is particularly useful for a specific type of algorithm called the quantum approximate optimization algorithm.
Yeah.
Why is that significant?
Well, that particular algorithm, it holds a lot of potential, right? It holds a lot of potential for tackling these real-world optimization problems. So think about things like finding the most efficient routes for deliveries or optimizing financial portfolios, things like that. The ability to entangle qubits over these longer distances, which this shuttling allows for, it makes Aquila really well suited for running these types of algorithms very efficiently.
So we're seeing here how the hardware design directly impacts the types of problems that Aquila can solve. It's not just about the number of qubits, but it's how they're arranged and how they're manipulated.
Exactly. The architecture is really a key factor in its potential.
Now let's talk about error correction. I know this is a major challenge in quantum computing, right?
Yeah.
Quantum states, they're notoriously fragile.
Mm-hmm.
How does Aquila kind of tackle this issue?
Yeah, you're absolutely right. Error correction is the bottleneck, I think, in the field right now. And what's exciting about Aquila's approach is they're using this specific type of error correction called topological error correction. Now, this method is a lot less sensitive to noise and errors, right? It's more robust, much more robust than these traditional methods.
Okay. Can you maybe explain how topological error correction works? It sounds pretty complex.
Sure. Imagine you're braiding strands of hair, right? So each strand represents a qubit, and the braid itself, it represents the encoded quantum information. So even if one strand gets messed up, right, the overall braid, the information it holds, it remains intact. And so that's kind of the basic idea behind topological error correction. It's encoding that quantum information in a way that's just very resistant to these small errors.
That's actually a really helpful analogy. So it's about protecting the overall information by distributing it across multiple qubits. That sounds like a very promising approach to tackling this error correction challenge.
It really is. And I think it's one of the reasons that Aquila is being viewed as such a significant step forward in developing these fault-tolerant quantum computers.
So it's not just about the hardware. It's also about the software and algorithms that work behind the scenes to ensure the integrity of these quantum states.
Exactly, precisely. And here's where it gets even more interesting, right? Aquila's not just a research project tucked away in a lab. It's actually accessible through Amazon Bracket, which means that researchers, even companies, can test its potential.
Oh, wow. That's huge. Schneppet mentioned some applications like optimizing telecommunications networks and exploring possibilities in drug discovery.
Yeah.
Can you kind of elaborate on those real-world applications a little bit?
Yeah, absolutely. So one specific example that Schneppet highlights is the optimization of a telecommunications network in Spain. And so Aquila was actually able to outperform classical computers in finding the most efficient way to route traffic through this network. And so, this kind of optimization, it can lead to faster, more reliable internet connections.
So we're already seeing tangible results, real-world results from this. That's pretty impressive.
Absolutely. And on the drug discovery side, right, Aquila is being used to simulate the behavior of molecules. And this could lead to the development of, new drugs and therapies for a wide range of diseases.
It's incredible to think about the potential impact this could have on healthcare.
For sure. And these are just a few examples, right? I mean, the possibilities are vast, and I think we're really just at the beginning of exploring what Aquila can do.
It's clear that Aquila is pushing the boundaries of what's possible with quantum computing. Mm-hmm. But what about the bigger picture? Where does Aquila fit into the overall landscape of, quantum computing research and development?
Right. Well, Schneppet, he makes a point of highlighting QuEra's collaborative approach, right? So they're partnering with universities, research centers, and even Google to kind of push the boundaries of quantum computing.
So it's not just about competition, it's about working together to advance the field as a whole.
Exactly. And that open approach, I think, is really crucial for accelerating progress and making sure that those benefits are shared widely.
It makes a lot of sense. It's a complex field. It requires expertise from so many different disciplines. So having that collaborative ecosystem, it can only be a good thing, right?
I agree. I think that collaborative spirit is really a key part of QuEra's vision for the future.
Okay, that's actually a great point to kind of transition into a discussion about the future of Aquila and quantum computing as a whole. But before we do that, I think it's time to take a quick break. We'll be back soon to continue our deep dive into QuEra's Aquila and the world of quantum computing. We've been talking a lot about Aquila's impressive capabilities and all, but I kind of want to shift gears a bit and talk about, what does this all mean for the average person? How might quantum computing and Aquila specifically, how might it impact our lives in the years to come?
Well, that's a great question. And while we're still in the early stages, I think Schneppet does hint at some really exciting possibilities. One area that I think really stands out is healthcare, right? We've already touched on drug discovery a bit, but quantum computing could really revolutionize medical imaging, diagnostics, personalized medicine. There's a lot there.
Yeah. Can you give us some concrete examples of how that might actually play out?
Sure. Imagine being able to detect diseases, like cancer at a much earlier stage using these quantum sensors, or being able to simulate the effects of different drugs on your specific, genetic makeup to determine the most effective treatment. These are just a couple examples of how quantum computing could really personalize healthcare and hopefully improve outcomes for patients.
It sounds like something out of science fiction, but it's fascinating to think about the potential. Schneppet also mentions applications beyond healthcare. In fields like material science, for example. What kind of impact could we see there?
Oh, material science, I think that's really ripe for disruption by quantum computing. Imagine being able to design new materials with properties that, we can only dream of today. Things like, lighter, stronger materials for aircraft, more efficient solar panels, maybe even self-healing materials.
Wow, that would be incredible. It sounds like quantum computing could really usher in a whole new era of technological innovation across so many different industries.
Well, I think so. And it's not just about, creating new things. Quantum computing could also help us solve some of the world's, most pressing problems like climate change.
Oh, really? How so?
Well, think about using quantum simulations to design more efficient renewable energy sources or to develop better carbon capture technologies. We could even use quantum computers to model the complex interactions of, the Earth's climate systems to gain a deeper understanding of climate change and hopefully, develop more effective solutions.
It's inspiring to think about the positive impact that this technology could have on our planet. Now, Schneppet also touches on the potential of quantum computing in artificial intelligence. Can you elaborate on that a little bit?
Right. AI, that's another field where I think quantum computing could be a real game changer. By combining the power of quantum computing with these AI algorithms, we could see some major breakthroughs in machine learning, natural language processing, pattern recognition.
So what would that mean in like practical terms for everyday life?
Well, think about virtual assistants that can truly understand and respond to complex requests, self-driving cars that can navigate seamlessly in all conditions, or systems that can, analyze vast amounts of data to make more informed decisions in real time.
It's a lot to take in. It seems like quantum computing could fundamentally change the way we live, the way we work, the way we even interact with the world around us. But Schneepat does acknowledge that there are some challenges and concerns that need to be addressed, as this technology evolves.
Right. He briefly mentions, potential for job displacement as automation becomes more and more sophisticated. I think it's something we need to think carefully about as we develop this technology and ensure, a just transition for workers who might be affected.
Yeah. And what about data security? I've heard concerns that quantum computing could potentially crack current encryption methods.
Yeah, that's a valid concern. Quantum computers are theoretically capable of breaking the encryption methods that, we rely on today. That's why researchers are already working on new encryption methods that are resistant to, these quantum attacks. It's crucial that we stay ahead of the curve on this issue.
It sounds like there's a lot of responsibility that comes with this powerful technology. It's important to consider not just the potential benefits, but also the potential risks, and to develop it in a responsible way.
Absolutely. I think we need to have, some open and honest conversations about the ethical implications of quantum computing and make sure that, its development and deployment align with human values.
It seems like QuEra is taking this responsibility pretty seriously. Schneepat emphasizes their commitment to, this collaborative approach and working with others to ensure the responsible development of this technology.
Yeah. They're actively involved in discussions about the ethical implications of quantum computing. They're working with, other companies, research institutions, policymakers to establish some guidelines and best practices for the development and the deployment of this powerful technology.
That's encouraging to hear. It's good to know that they're not just focused on, the technical advancements, but also on the broader societal impact.
Right. I think they understand that this technology has a potential to be, really transformative, and they want to make sure that it's used for good.
Well, before we get too deep into the future of quantum computing as a whole, I want to kind of bring it back to Aquila specifically. Schneepat mentions QuEra's roadmap for future development. Can you tell us a little bit more about their plans?
Sure. One of their main goals is to develop what they're calling third-generation models of Aquila. And so these models would actually feature these logical error-corrected qubits, which would be a major step forward.
Yeah, I remember you mentioned logical qubits earlier. Can you just remind us what those are again and why they're so important?
Right. Think of physical qubits as like the raw materials, right? And then logical qubits are like the finished product. So they're built by combining multiple physical qubits and applying these, really sophisticated error correction techniques. And this creates a much more stable and reliable qubit, which is really essential for building these more powerful and fault-tolerant quantum computers. So
it's like taking those individual Lego blocks and assembling them into a complex structure that's just much more robust.
Exactly. And with logical qubits, we can start tackling, much more complex problems and developing these practical applications that can really have a real impact on the world.
It sounds like QuEra is really pushing the boundaries here of what's possible with quantum computing. But they're not just focused on the hardware, are they? Schneepat also highlights, their work on hybrid quantum classical algorithms.
That's right. I think they recognize that we're not at a point yet where quantum computers can just completely replace classical computers. And so these hybrid algorithms, they really allow us to leverage the strengths of both types of computing.
Can you give us an example of how that might work in practice?
Sure. Imagine you're trying to design a new drug. So you could use a classical computer to simulate, the overall structure of the molecule. And then you could use a quantum computer to simulate these very, very specific interactions between atoms at the quantum level. And so this hybrid approach, it allows you to tackle problems that would just be, impossible for either type of computer alone.
Oh, I see. So it's like having a team of specialists, right?
Yeah.
Each with their own unique skill set, working together to solve a complex problem.
Exactly. And this hybrid approach, it's already showing great promise in, fields like optimization, machine learning, and material science.
It's really fascinating to see how this technology evolving and how QuEra is finding, these creative ways to apply it to real world problems.
And it's just the beginning, As quantum computing continues to develop, I think we can expect to see, even more innovative applications emerge, in fields that we haven't even considered yet.
It's clear that this is an incredibly exciting time for quantum computing, and QuEra, with its Aquila system, is really leading the charge.
Mm-hmm.
But before we get too carried away with all these future possibilities, I kind of want to bring it back to the present and talk a little bit more about the current state of Aquila. Schneppat mentions that it's accessible through Amazon Bracket. What does that mean for researchers and companies that are interested in, actually using this technology?
Well, it means they don't need to build their own quantum computer to start experimenting with this technology, right? They can access Aquila remotely through the cloud and run their own, algorithms and experiments.
So it's kind of like a quantum computing playground where researchers and companies can test out their ideas and really explore the potential of this technology.
Exactly. And I think that kind of accessibility is crucial for accelerating progress and driving innovation in the field, right? It allows researchers to test their theories, companies to explore new applications, students to gain, hands-on experience with this cutting edge technology.
It's amazing to think about the possibilities that this opens up. We've talked about a wide range of potential applications, but I'm kind of curious to know, what do you personally find most exciting about Aquila and the future of quantum computing?
For me, it's the potential to unlock a whole new realm of scientific discovery. There are so many mysteries in the universe that we simply can't solve with classical computers, right? And so I think quantum computing gives us this new tool to explore these mysteries and potentially, make breakthroughs that could really revolutionize our understanding of the world.
Yeah, that's a great perspective. It's not just about technological advancement. It's about expanding our knowledge and understanding of the universe that we live in.
And who knows what we might discover along the way, right? We might find solutions to problems that we haven't even thought of yet, or develop technologies that we can't even imagine today.
It's truly an exciting time to be following this field, and it's clear from Schneppat's essay that QuEra is playing a key role in really shaping the future of quantum computing.
Absolutely. They're not just building quantum computers, they're building a community, fostering collaboration, pushing the boundaries of what's possible.
Well, we've covered a lot of ground in this deep dive, from the technical intricacies of Aquila to the far-reaching implications of quantum computing as a whole. Before we wrap things up, I want to kind of give you the last word. What key takeaway would you leave our listeners with? Well, I would say that quantum computing is, it's no longer a futuristic fantasy, right? It's here, and it's evolving rapidly. I think QuEra's Aquila is a prime example of the incredible progress being made in this field. While there are still challenges to overcome, the potential of this technology is truly transformative. I think it has the power to reshape industries, solve global challenges, and really deepen our understanding of the universe. It's an exciting journey, and we're really just getting started. Well said. I think that's a perfect note to end our deep dive on. We encourage you to continue exploring the world of quantum computing and stay tuned for more exciting developments in this revolutionary field. This is the deep dive signing off. We've spent the last couple segments really digging into the nuts and bolts of Aquila, but I want to kind of step back for a minute in this last part and think about the big picture. Schneppat paints this really compelling vision for the future of QuEra and quantum computing in general.
He really does. One of the things that really struck me was QuEra's commitment to making this technology accessible, right? Like Schneppat talks about their roadmap, and it's clear that they're not just focused on building bigger, better quantum computers. They're thinking about how to make them useful for a wide range of, people and applications.
Right. We touched on how Aquila is already available through Amazon Bracket, which, lets researchers and companies kind of experiment without needing to build their own machine. But where do they go from there?
Well, he mentions plans for, what they're calling third generation models of Aquila. And this is where, those logical error-corrected qubits that we talked about earlier, this is where those come into play. And that's going to be a game changer, I think, for the complexity and reliability of the computations that they can perform.
Yeah, I remember you comparing those logical qubits to like the finished product, right?
Yeah.
As opposed to like the raw materials of the physical qubits. But even with better building blocks, writing effective quantum algorithms just seems really difficult.
It is. And that's why I think, Schneppat's emphasis on QuEra's work with these hybrid quantum classical algorithms, I think that's really interesting. It's kind of a way to bridge the gap between where we are now and where quantum computing could take us in the future.
Can you remind our listeners why that hybrid approach is so important?
Sure. It acknowledges that, quantum computers aren't going to replace classical computers anytime soon, right?
Okay.
We're still figuring out how to program these machines effectively, and there are a lot of tasks that classical computers are just better at, frankly. And so the hybrid approach allows us to, use the right tool for the right job.
So instead of like an all or nothing approach, it's about combining the strengths of both classical and quantum computing to kind of tackle a problem.
Exactly. It's like a duet, right? Where each instrument plays its part to create this harmonious whole. And Schneppat even mentions, QuEra's success in optimizing these telecommunications networks. I think that's a perfect example of how this hybrid approach can actually deliver, real world results, right now.
It's exciting to see how these theoretical advancements are being translated into these, practical applications. But Schneppat also kind of leaves us with this very open-ended question,
Yeah.
What stands out to you as the most promising aspect of this technology? It's an invitation to kind of think about the bigger picture and how quantum computing might shape our world.
Yeah, I think for me, it's the potential to solve problems that are simply beyond the reach of classical computers, right? We've talked about, drug discovery, material science, but there are so many other fields that could be transformed, right? I mean, everything from financial modeling to climate science, could potentially benefit from the power of quantum computing.
Yeah, it's almost overwhelming to think about the possibilities. It feels like we're on the cusp of this technological revolution, and QuEra, with its Aquila system, is kind of leading the charge.
I think that's a fair assessment, yeah. Schneppat's essay, I think, highlights not just the technical ingenuity of QuEra, but also their vision for this collaborative future, right? It's not just about building, the most powerful machines. It's about making sure that this technology actually benefits everyone.
Well, we've reached the end of our deep dive into QuEra's Aquila, and it's clear that, we've only scratched the surface. Schneppat's essay has given us a lot to think about. As he eloquently concludes, we are witnessing the unfolding of this quantum computing era, and Aquila is this shining example of what human ingenuity can achieve. It's an exciting time to be alive, and we can't wait to see what the future holds for this groundbreaking technology.
I completely agree. And I think, his essay is a call to action, really, for all of us to engage with this emergent technology, to learn about it, to ask questions, and to be a part of shaping its future. The journey of discovery has just begun.
And on that note, we'll wrap up this episode of the Deep Dive. We hope this deep dive has been informative and thought-provoking, and we encourage you to continue exploring the fascinating world of quantum computing.
Thank you for listening.